All right. Fair warning, I'm going to end up probably just coughing through most of the class. I don't really feel bad, but I can't stop coughing. So chances are I'll get all of you sick, and you probably deserve it. Because one of you more than likely got me sick. What was I talking? Oh, so as a review, last time we were talking about similarity between blockchain and computer science, and some different ways we can approach the blockchain in terms of distributing it or not distributing it. Right at the end of class, I mentioned, I think I asked the question, is it good for us to distribute it? Is it good for us to approach the blockchain like a linked list versus an array? And I think kind of as we were walking out, we said, well, maybe not, because now we have to protect a whole bunch of individual pieces of it, right? And even the loss of one piece of data potentially means the loss of all the coins. We can't have a break in the chain. So having one gigantic chain might actually be a necessity for the blockchain. So something for us to consider. We already talked a little bit about application-specific integrated circuits. So these are computer chips specifically designed for mining Bitcoin or mining any sort of coin. We talked about hashing being fast. Bitcoin has a requirement that each block is validated in approximately 10 minutes. So if blocks start being done quicker than that, we need some way of making it more difficult. Otherwise, every Bitcoin that would ever exist would be mined in a matter of minutes. So we have something called proof of work for Bitcoins. And actually, this is for any cryptocurrency based on the SHA-256 algorithm. So the Bitcoin network won't just accept any hash. It demands that it look a certain way. That is, it has to have a certain number of zeros out front, blah, blah, blah. The network will only accept a hash with a certain number of zeros at the beginning of it. There's no way of determining what a hash will look like before you produce it. Kind of an interesting piece of information related to hashes. So even a small change will result in a very, very different hash. On top of that, when we make a hash, when we make our guess, we incorporate into it a nonce, which is just a random value that's generated on a per guess basis. So miners are not allowed to change the data that's actually in the block. Part of what is being put together to create that hash is the block data itself. Well, we can't change that. As miners, we can't modify that. We also can't change the previous block's hash. That's already fixed, set in stone. So we also need to create a hash in the correct format. So we add another small piece of information called the nonce, which we can base off of a lot of different things. Usually we base those off of the number of seconds since 1970, which is a kind of a random, well, I say random, it's a time interval, but it's number of seconds since 1970. And let me ask you this. Does the nonce need to be more random than that? So for instance, if I do one guess per second, that means the nonce, let's just use simple numbers, the nonce would be 1 this second, 2 the next second, 3 the next second, 4 the next second, so the nonce isn't random at all. Is that a problem? Remember, all this stuff is going into the cookie batter that's making a guess, a hash. Does the nonce really have to be random? Go ahead.
No.
Okay. And why not?
Because you don't know what it's going to look like. So it could look like the ending result of the hash could be anything. So it doesn't really matter.
Okay. So I could have a completely non-random nonce, or I could have a completely random nonce, and I could very likely get, very random looking hashes, correct?
Yeah.
Can I always use the same nonce? Could I just use one every single time as my nonce?
It would kind of defeat the purpose of having nonce.
Well, if nothing else changes in the hash. We're going to go back here for a second. just go here. So if this is the stuff that goes into a hash, so the version number, this is a fixed number that the miner can't change. The hash of the previous block, also a fixed number we can't change. The hash was something called the Merkle root, which is the current block itself, but more of its header information as opposed to the actual data within it. The current timestamp in seconds since 1970, so this could have been used as a nonce, but whatever. Bits, current target in compact form. We'll talk about the target in the next slide, but the target is kind of it's the answer. So we know the answer beforehand. And then the nonce, 32-bit number, starts at 0, increments each time. So the only two moving parts in here are the time estimate and the nonce itself, correct? The answer remains static. The hash of the current block's header remains static. The hash of the previous block remains static. And the version number remains static. If we use a hash to do if we try to hash the block header with the exact same time and nonce, we will always get the same answer, correct? So at the very least, those two things need to change. Time is incrementing, the nonce is incrementing. That's what produces different hashes. Now, what keeps us from having more than one person hashing the same, doing the same guess? Go ahead. Estimate. So if we're all mining, and we're all meant to give our guess, and let's say we're all the exact same speed, randomly, right? So we have millions of miners out there, and they all are going to have some hardware that is going to be operating at different speeds, but there's going to be plenty that are going to be potentially guessing at the exact same time, right? That means that their time since 1970 would be identical, and their nonce very likely might be identical if we all start at 0. Just keep incrementing by 1 every guess. That's not necessarily every second, it's every guess. Correct? So what keeps you and me from having the identical guess? Or at least, how would you solve that problem? If we're all trying to guess to break this, to show our proof of work for this, there has to be a clear winner, right? We're all trying to guess, trying to hit the target. But what keeps you and me from having the exact same guess?
You're not talking about being a pool.
Doesn't matter if we are dealing with pools or miners. Because we can think of a pool as a miner. They just happen to be a miner with a bunch of guesses, a bunch of horsepower.
Let's talk about the individual people in the pool. Because we talked about that previously, about how we would do that.
I get what you're saying. But for this question, it doesn't really matter who we're talking about, whether we're dealing with individual people within a pool, making sure they don't have the same guess, or a person that's in one pool against a person who's in another pool. We need to make sure people don't have the identical guesses at the exact same time. Because that would be a waste, right? There has to be a winner. We can't have a tie. Does a guess mean anything? It's not like we're solving some math problem or anything like that, right? It's not like there's no such thing as doing the math wrong. It's just a flat out guess. What number am I thinking of? And then we all just start spitting out numbers. Well, if we all start with the number 1, everybody in here is going to guess 1, then everybody in here is going to guess 2, and everybody in here is going to guess 3. That's not random, right? So you guys are all stumble upon it at the same time. So when a miner checks out work, there has to be something about what they just checked out that's unique to them. Okay?
Nonce value.
The nonce value isn't necessarily unique to them. The nonce value is going to be unique to them per guess. So unique within themselves per guess. So the first guess might have a nonce value of 0, then 1, then 2, then 3, then 4. But that's only within themselves. Because within themselves, if I'm making guesses, the thing that's changing is the time and the nonce. Why do we need both of those? Why do we need the time and the nonce?
And security and tracking. So you can see who did what.
Just within yourself. So don't even worry about the rest of the competition. So you are making your guesses. Why do you need the time and the nonce? Why can't you just work off the time?
The nonce, you can count how many guesses you do in certain time.
True, the nonce you can count, but why do we need that? Is it just for extra information for us?
No, it's security, I think. You can, if a miner can, I don't know, it's every time is, no, it's, hits the right hash in the first, or I don't know, the first nonce, it's something wrong.
So let's say that you have some sort of math algorithm for figuring out a hash. But it's a math algorithm, so it's always going to produce, given the same inputs, it will always produce the same output, right? So I'm going to give you a hard-coded version number. I'm going to give you a hard-coded previous block hash. I'm going to give you a hard-coded Merkle root value of the current block. I'm going to give you a time, which is the number of seconds since 1970. I'm going to give you the current answer, which is the current target in compact form. It's 4 bytes. And I'm not going to give you a nonce. So let's take the nonce off here, and then we'll see why we need a nonce. So I'm going to tell you to, given those, 1, 2, 3, 4, 5 inputs, make a guess. You're going to feed the stuff through your math formula, right? And you're going to come up with a guess. And then we're going to check that guess to see if it's right, whatever that means. And let's say I say it's not right. I want you to guess again. So what are you going to do to guess again?
Well, the time will change.
Will it?
I mean, if it changes every second, continues, your time is going to change. If you make a guess 3 seconds later.
Would you be happy if your computer can only do something once per second?
No, it's not efficient at all.
It's slow, right? So time is only adjusting every 1 second. So that means if we can make, let's say we can do 1,000 guesses in a second. Just throwing that out there, right? That means using that algorithm without a nonce, we would literally make the same guess 1,000 times in a row before the time adjusted up by 1 second. That make sense? That's why we need 2 separate variables. The nonce allows us to make guesses within a second before time changes. Because we'll make the first guess with a nonce of 0, the second guess with a nonce of 1, the third guess with a nonce of 2, the fourth guess with a nonce of 3, so on and so forth. Go ahead.
What's the, if you're going to do that, do you need a time stamp then? Or is that just added in to make your...
Oh, so you're looking at the other side. Maybe we get rid of the time. Okay, tell me why that's a bad idea. So he's arguing like, well, let's dump time. Let's just go with the nonce.
Because I got nothing.
You got nothing. Well, why can't we do this with just a nonce? Why is that a bad idea?
Your nonce just go up like infinitely, incredibly high. I mean, not that it doesn't already like do that anyway, but then you don't really have, because otherwise now you have like time is 0, just even though it's definitely not 0, and then your nonce is 0, your nonce is 1, your time is 0, because you're still like in 1 second. Now you don't really have that extra like your nonce will just go up forever basically until you get it right.
Was that okay? Why is that bad?
There's a limit to the 32
Yeah,
bit.
it's 32
and then
Oh, interesting. What is that limit?
2 billion.
plus or minus 2 billion.
Plus or minus 2 billion. So to show you this on a, what happens? What happens once I get to the 2 billion and I try to add 1 to that?
Bad
The world just ends? So 0, 1, 2, 3, 2 billion, and whatever, poof.
It's kind of like just having time that you make the same guess, and then if they you gotta wait until the next second, and so it really makes the problem unsolvable if you go through all of them and you don't find a solution. Having a time can change the possible solutions.
Okay, but I want to know specifically why having just a nonce is bad. So we're going to, per Abe's suggestion, the patriarch, we're going to dump the idea of time and just keep a nonce, which is a 32-bit number.
before the, if you do that, then the 10 minutes would be up before you got the 2 million guess, before you guess the 2 million times. So then
2 billion times? Is that what you mean? 2 billion times?
sure, yeah.
I mean, sure, yeah.
Yeah,
Why is it 2 billion instead of 2 million?
because that's what it is.
Well, what is?
32-bit.
32-bit? Why? How did we just come up with that 2 billion number?
Because that's how big it is.
Okay, why? How did you figure that out besides just taking my word for it? What's the math behind it? The range of values that fit inside of an integer, which is 32 bits, is plus or minus 2 to the what? Plus or minus 2 to the 31st power. So 2 to the 31st power is 2 billion something. Here we'll... What's that? 2,147,483,648, and decimal place on the other side. So that's why it's plus or minus 2 billion. Well, what happens as I count up to 2 billion and I hit 2 billion and 1?
So that variable can only hold the 2 billion or whatever bucket,
Yep.
and then it's full, and you just try to add to a full bucket.
Okay, and what happens? Is that when time and space collide? Let's do this at a little bit smaller scale. Let's use a byte. So byte B will start off at 0. And what's the biggest value we can store in a byte? Plus or minus 2 to the what? 7. Because one of the bits is used for the sign. For positive and negative numbers. To be honest, I'm not certain whether this nonce is a signed or an unsigned number. Doesn't really matter for right now. Let's just assume it's a signed number, which means it can be positive and negative. But we're going to start at 0. So, if I do a little loop for int I equals 0, I is less than 120, I plus plus, I do system.out.println b, and then I say b is equal to b plus 1. Oh, it doesn't. That's funny. So we're going to print out the current value of b over and over again and add 1 to b each time. And this is going to get us from 0 to 119. Let's let it go all the way up to 127. This is 126. Let's let it go to 128. This is to 127. Now what happens if I let it to go to 129? Oh, the minimum byte value. It'll roll around. What's the smallest byte value? Negative 128. So the byte value 127 plus 1 is negative 128. Make sense? All right. So, sorry. So, why is using just a nonce a bad idea? Just keeping with this argument. If my nonce is only an 8-bit number instead of a 32-bit number, after I make 128 guesses, what happens?
Start guessing the same thing.
I make the same guess again. In this case, it's actually 256 guesses, but you get the point, right? And is it reasonable to think that a computer could be fast enough to make more than 256 guesses in a second? Could a computer make more than 4 billion guesses in a second? Certainly possible, right? So that means that this is all happening within 1 second. Within the same second, I might have duplicate guesses. Now, having said that, remember, we're getting rid of time. Is it completely probable that a computer is going to make well over 4 billion guesses in a relatively short period of time? Let's say it takes us 10 seconds. Well, that means after 10 seconds, we're going to start making guesses we've already guessed before. That make sense? That's why we need those 2 separate values. But even within that, there's a problem. Is there a possibility with having 2 separate values, the time and the nonce, that we might guess the same thing twice in a row? Well, not twice in a row, but twice.
Yes.
How?
Because if you guess whatever that number was, 4 billion, where you're saying it's signed or unsigned. If it's unsigned, if you guess like 4 billion, then now you're going to roll back like you just showed, right? Or at least have a chance to.
Mm-hmm.
That could happen in less than a second. That's reasonable to think. So.
Or at least it doesn't seem impossible.
Yeah.
So if our computing, so ASICs in this case, application-specific integrated circuits, if they start building machines that can make so many guesses within 1 second that we run out of unique nonces and nonce swirls back around before time actually increments by 1, we're going to be making duplicate guesses. So there's actually a theoretical maximum speed that an ASIC could be, given this value. Could we fix that? How? What do we do if tomorrow they come out with a computer, ASIC miner, that can make more than 4 billion guesses in a second? In fact, actually, let me just see where we're at right now for that. So our fastest single machine, probably do 3 terahashes. Let's just say that. So that's 3 times 1024. That's gigahashes times 1024. That's hashes. So that's 3,145,728 guesses per second. So 3.15 guesses per second is what our fastest single piece of equipment is. Okay, so we're kind of safely under the 4 billion mark right now. But theoretically, we could get up to faster than that, right? Well, how does it work? Let's see, what's the let's look at let's see what their current speed is. This is the biggest mining pool right now. And they can't update their logo to the current year. 50.78 petahashes. So 50.78 times 1,024 gets us to terahashes, times 1,024 gets us to gigahashes, times 1,024 gets us to hashes. That's, is that 54 billion? 54,524,609,823. So 54 billion guesses per second is what's coming out of this particular pool. Now the good news is each person in that pool is getting a unique value that makes their guess, differentiates their guess from somebody else's guess, potentially at least, right? So we don't have overlap there. But if any individual person had a computer, had a single device that could make more than 4 billion guesses in a second, they actually just wasted horsepower. So there's a theoretical speed of light, if you will, for guessing. But is that easily solvable with the current algorithm?
Well, could you just fake the timestamp and start incrementing the timestamp yourself instead of waiting for it to increment itself every second? Like start going every half second?
Well, not for the timestamp, but you can add another nonce. So you could have 2 bits of nonce. So once you hit 4 billion, the nonce that was staying at 0 now became 1. 0. All the way to 4 billion, now it's 2. 0. Now it's 3. 0. Now it's 4. So you can just add another nonce here. But now you're changing the dynamics of the algorithm. You're adding another variable in there. What else could we do? What would be the easier, similar but easier solution to this problem? Make the nonce bigger. Maybe make the nonce 64 bits, 8 bytes instead of 4 bytes. But wait, doesn't that break everything? Isn't that going to screw up our guess if we're giving it a 64-bit number instead of a 32-bit input?
Can change the variable.
Okay.
4 bytes.
But doesn't this stuff need to all remain the same in terms of input size in order to have like hashes in the correct format? It's a trick question. Won't me changing our nonce from a 32-bit number to a 64-bit number give me a hash in a different format?
Well, no,
Why?
because the hash is a set size.
Hash is set size. A hash is an arbitrary size input with a finite size output. So if I want to throw more data into it, no biggie. In fact, realistically speaking, every single time through, our block is likely going to be a different size. I mean, you might run into 10-minute increments where you have number of transactions that are the same as another 10-minute increment, but the chances of having 2 10-minute increments in a row with the same number of transactions is slim to none. Certainly, the chance of having 2 blocks in a row with the same number, with the same identical transactions is nearly impossible, right? So the input here is arbitrary in size. You might have a block where there was 2 transactions. You might have a block where there was 2 million transactions. You're still going to get a 32-byte 32-byte digest hash. So it doesn't matter how big the input was. It doesn't matter how big our nonce is. If 64 bits isn't enough, make it bigger. Just keep counting. Now we do have an issue when it comes down to the math of this. So this starts becoming a bottleneck type discussion. We do have a 64-bit number in Java, or any other modern day language, called a long, right? Long is plus or minus 2 to the 63rd power. The range of values it holds. And let's see what that value looks like. That. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So it'll be 3 more after that. So these are, just treat these as all zeros and remove the decimal point. That's the numbers.
Is there a way to do it without having ET18?
I don't know if there is in there's probably a number formatter you can use.
Is it what's making it? Is it the math?
Yeah, this is just how to represent it in scientific notation. So let's see here. So it's thousands, that's millions, that's billions, that's trillions, that's quadrillions. So this is 9 quintillion, 223 quadrillion, 372 trillion, 36 billion, 854 million, 776,000. So plus or minus 9.2234 quintillion is the size of a long. So we're safe going to 64-bit numbers as long as we can't do that many guesses in a second. And we laugh now, but can we with 100% accuracy say we will never get computers that are that fast? Who knows? Especially when you deal with a problem like this. Potentially, could our modern day ASIC miners, application-specific integrated circuits, could we potentially make one that can make that many guesses in a single second?
Yes.
How?
By adding a lot more ASICs chips.
Lots of chips. I mean, you might have to put it on a board the size of a football field. Maybe bigger, probably bigger. If we took chip after chip after chip and linked them all together and put enough power into it to actually run that, you could potentially come up with enough guesses, right? To make it happen that fast. It'd be giving off a lot of heat too. Probably want to do this in like Antarctica.
Melt Antarctica.
Huh? Melt. Yeah, all of a sudden, I'll show you global warming. What's this?
Hook it up straight to the power plant.
That's right. Well, there actually probably wouldn't be enough power. And they sort of, that would bring down the grid in the United States, I'm sure. So, theoretically possible. But you're talking about a pretty serious Bitcoin mining machine. Okay? Because right now the limitation, probably the fastest single machine you can order is about 3 terahashes. That's about, I don't know, probably $9,000 or $10,000 for that single machine. And maybe it's the size of a couple shoeboxes stacked on top of each other with big fans all over it. Anything bigger than that, all of a sudden it becomes difficult to ship. Now, you might have hobbyists. You might have hobbyists who build it themselves, right? So they have out in their garage, they have some sort of, death machine. They're powering the thing off kerosene. But realistically speaking, we aren't filling up our computational problem. We don't have a computational problem now. But foreshadowing, we could see we could have one. This is actually kind of an interesting dilemma. So we just saw here that nothing in the Bitcoin algorithm prevents us from getting machines faster and faster and faster and faster and faster. Our hardware isn't there yet. but it keeps getting faster every week, let's say. Which means the stuff from 3 months ago that used to be awesome is now crap. That's now half the price it used to be because it's not fast enough anymore. Is that a problem in and of itself? Why does somebody mine Bitcoin? Remember back to our early chart. All the players in the cryptocurrency world. Why would you personally choose to mine Bitcoin? Why would you plug a machine into your wall, taking up your electricity, making you pay a power bill? Why would you do that to mine Bitcoin?
Because you're interested in it.
Oh, just hobby? Like, oh yeah, just, I'd like to give the power company more money just because of a hobby. Go ahead.
Because you want to win the 25 Bitcoins.
Or you're a fraction of it, right? You want Bitcoins. So you're going to spend US dollars on a piece of equipment, and then you're going to give even more US dollars to the power company for that piece of equipment to work with the hope that you gain Bitcoin as your reward for mining. So you're not altruistic. You want to be paid. Right? You want to be paid. So now you're earning Bitcoin from that thing. Well, how much Bitcoin do you get?
How are you putting
Your fraction of the 25 Bitcoins based on the amount of work that you did in the pool that you're mining with only when they actually win. So if you're in the biggest pool and the biggest pool is winning 40% of the time and you're the tiny, 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 tiny fish in that pool, you're getting some fraction of a fraction of a fraction of 25 Bitcoins 40% of the time. That's what you get. Well, is it good that our equipment keeps getting faster and faster? Well, for whoever has the current, newest, best equipment it is. Same thing happens in video games with our home computers, right? How many of you have built your own video game rig at home? A great graphics card in it, stuff like that. Any of you ever build one of those and then you thought it was the greatest thing ever, and then 6 months later, some kid down the hall has one that's even better? He didn't even know what he was doing. Yours is crap now. You could eBay it for a tenth of what you spent to build it. It's antiquated, right? Mostly because of the graphics card. So you can sort of kind of keep up with the Joneses by just keep upgrading your graphics card for at least a certain period of time. But the same thing happens. And then what happens? The new video games come out? Well, video games usually take programmers 2 or 3 or 4 years to write. So when they start working on a game, they basically try to just guess how fast computers will be. Like, okay, well, we're going to make graphics that will not even come close to working on modern technology. Because by the time this game is done, we want it to kind of just barely work. Right? Every new game that comes out, the bragging rights is who can play the game with everything turned all the way up. Right? That's I have all the textures down to medium. We get the best rig out there. Yeah, this game is ridiculous. So, the same thing happens with Bitcoin mining equipment. But with this, the problem's even bigger. Because now you have invested in mining equipment, you're paying your power bill, but now you're making less Bitcoin off of it. So the amount of Bitcoin you made a month ago is going to be less than the amount of Bitcoin you'll make this month. Because the difficulty of the Bitcoin network went up, because the current mining power went up, which means that it was taking less than 10 minutes for each block to be mined. So your profits keep going down, 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 to the point where all of a sudden you're not making enough to cover your power bills. So if you're not making enough to cover your power bills, what's going to keep you mining Bitcoin? Just because you're interested?
Depends on how much excess cash you have.
How interested and how willing you are to just throw cash away, right? This in and of itself is actually a weakness, as I see it, of the Bitcoin network. The Bitcoin network requires those miners are there. They have to be part of the equation. Well, are we at risk of losing Bitcoin miners? Are we at risk of losing all the Bitcoin miners? No, just the crappy ones. There's high turnover, right? The guy who was awesome 6 months ago now is stuck with all this equipment that can't keep up. So now we have new people who've come in who spent the same amount of money, US dollars, that guy spent 6 months ago, but now they have equipment that's 3 times faster than his. So they really just keep kicking people to the curb. It's a very thankless type of thing to get into. But are we really at risk of losing all the miners? What are we at risk of? Seems like there will always be miners, correct? But right now, any of you could go out, use your graphics card in your computer. You don't have to go out and buy anything special. And you can mine Bitcoin. Set it up tonight if you want. And you'll just be, if you're in the dorms, Concordia's paying your power bill. You can run it off your graphics card. It'll probably give off some heat, but you can start mining Bitcoins. Now, the graphics card is going to mine Bitcoins really, 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 really slow because of these application-specific integrated circuits. But you can even jump on Amazon, buy a 3 or 4 gigahash per second. So 3,000 guesses. Well, no, actually, 3,000 times 1,000. What's that, 30,000? 300,000. 300,000. 300,000 guesses per second. A little USB stick, looks like a jump drive. $20 off Amazon. Plug in your computer, go to town. That takes up like no electricity. Even that won't get you anywhere. The time it'll take you to make your $20 back is probably a year. Because you're operating at such a slow speed relative to the rest of the Bitcoin network. So you can just keep going out and getting better and better equipment and not being able to keep up. Is it problematic that the network keeps getting faster and faster?
For the little guy, yeah.
Really for almost any guy, but certainly most for the little guy, right? You're going to start seeing commercial places, and you already have seen this, creating their own Bitcoin mining scenarios where they have all this equipment, and they might even rent the equipment out to people. There's this whole new industry called cloud mining, where you can buy a fraction of their mining power. So there's places like that do it, but you're really seeing it become more commercialized. It's going away from the people just doing it out of their dorm rooms. In the early days of Bitcoin, if you had your graphics card today, like yours, you probably could have generated, probably a couple Bitcoins a week. So 2 Bitcoins a week, 8 a month, a high of $1,500 per Bitcoin, all on Concordia's power bill. Pretty legit, right? Pay for school. But you missed the boat on that one. Okay. Now your graphics card, which would have been completely epic in the early days of Bitcoin mining, when people were just mining Bitcoins using their CPU, is now ridiculously crap. Like nowhere near worth the electricity to run it. Except for 5 minutes just to say, oh, this is cool. Like, oh, I'm mining Bitcoin. And then you get your first payout. Well, you can get your first payout, so then, any one of you in here could set up your computer to mine Bitcoin, run it for a day, so that, with one of the pools, and chances are your pool would win once in that day, and you'll get your little tiny, 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 tiny payout. You are now a Bitcoin owner. I have 0.000000001 Bitcoin. But you're a Bitcoin owner.
That's more than
Right. So, it's actually viewed as one of the weaknesses of the Bitcoin technology that some of the altcoins attack. So Script is a competitor of SHA-256, and let's talk about the high level here for a second. And one of the main advantages of Script, just at the high level, is it was what was called ASIC resistant. Application specific integrated circuit resistant. So as Bitcoin mining gets out of control, where every 5 minutes companies are coming out with their newest, latest, greatest piece of mining hardware, they each keep just one-upping each other. Just like NVIDIA versus ATI for graphics cards. Whoever came out with the latest, from KNC Miner versus Butterfly Labs, whatever. There's 3 or 4 different big companies that do this. Whoever has the latest one, that's the one that's probably the fastest. All right? And they just keep one-upping each other over and over and over and over again. And the chips keep getting smaller and smaller. The current cool kid on the block is a 20 nanometer chip. Well, Intel's already making 8 nanometer chips. There's already technology in the middle that we can start bridging that gap. So they're just going to keep getting smaller and smaller and smaller, and more powerful, and taking up less and less energy. So the problem with Bitcoin mining power getting faster and faster isn't going anywhere anytime soon. It's going to keep getting faster. So one of the things about Script is it was said to be ASIC resistant. But that even only lasted for a little bit of time. Now there are ASICs for Script mining. Now you cannot mine Bitcoin with a Script miner. You have to mine coins that are based on the Script protocol. So one of those is called Litecoin. Litecoin is based on Script. So is another one called Dogecoin. And a bunch of other ones. But even this is getting out of hand. Now there's places that are coming out with super crazy fast Script miners. So what's going to come out next? All right, so is that actually an issue? When we have new technologies like Script coming out, trying to supplant, let's call it the adopted cryptocurrency, Bitcoin, because of the weaknesses in the, let's call the weakness, the weaknesses in the algorithm, does that actually make Bitcoin at risk of going away? Let's say tomorrow Microsoft came out with a brand new smartphone and it was awesome. Would they put Apple out of business? Would they put Google out of business with Android? Would they very likely not even make a dent, regardless of how good it was? And that's Microsoft. Too little, too late, right? So now we just need to find ways to build infrastructure around Bitcoin to regulate that problem. Maybe we create, regulations amongst the hardware manufacturers so that the equipment doesn't keep getting faster and faster. We put some sort of cap on the total number of gigahashes that can be, total number of guesses that can happen per second across the entire network. Almost distribute it like IP addresses on the internet. So these all become interesting problems. When we come back on Monday, we're going to create a data structure in Java for our block header. We're then going to create a fake hash algorithm of our own that literally just does random numbers. Okay? And we're going to create a scenario of making guesses until we get the right number of zeros. And we're going to see, even in an insecure situation, how many guesses it actually takes to hit the right number when your guess is a 64-bit guess. Okay? All right, have a good weekend. I'll see everybody on Monday.